This video presents the Penelope Horizon 2020 Project's Aeronautics Demonstration. Led by GKN Fokker Aerospace, the aeronautics pilot line focuses on the advanced assembly of the lower fuselage, integrating a digital pipeline to manage complex composite components for flexible, precise manufacturing. Within Penelope, GKN demonstrates their cutting-edge work in aerospace manufacturing. From advanced composites to innovative assembly processes, GKN is pushing the boundaries of technology to create lighter, more efficient aircraft components for a sustainable future in aviation. The Clean Sky 2 multifunctional fuselage demonstrator with its 8-meter-long composite-made fuselage section is the reference product for the samples used within the aeronautics pilot line. This demonstrator achievements in the Penelope project are made possible through collaboration with key partners: Unimore, K-Loops, SAM-XL, TNO, Airborne, KVE, ESI, NLR, and GKN Fokker, driving innovation in advanced aerospace manufacturing. Unimore has worked on the simulation of the aeronautics pilot line in a virtual environment using the RoboDK software. The assembly sequence is defined in the Penelope digital thread system. For each integrated system, a module is created and the operations to be performed are defined in the modules. An automation ML file is exported, interpreted by a Python script, and transferred to the simulation controller built in the ROS2 framework. The simulation is executed according to the defined sequence. It includes steps such as measuring the skin thickness by the TNO direct velocity mapping scanner, positioning of the stringers in the inner surface of the fuselage, induction welding of the stringers, NDT of the welded stringers by direct velocity mapping. Finally, cobots are installing temporary fasteners after drilling and installing permanent fasteners, also replacing the temporary ones. K-Loops developed a real-time system able to improve the absolute accuracy of industrial robots, especially in large workspaces. A laser tracker is used to continuously monitor the position of the tool attached to the robot during its job. Once the user defines the job through the application interface, the system takes control of the robot, generating real-time compensated trajectories on the base of the laser tracker feedback. Such system significantly reduces path and positioning errors, as clearly shown in the plots generated using the data collected by the application. SAM-XL is a center of expertise for automating large manufacturing processes, forming a unique liaison between the faculties of the Delft University of Technology, Industry, and suppliers. We develop software and hardware to enhance industrial robots' intelligence, connectivity, and flexibility. For the aeronautics pilot line, a zero programming framework was developed focusing on modularity, scalability, and flexibility. The industrial robot scans multiple panels inside of the jig, using a 3D camera to create a digital representation of the object. Along the reconstructed surface, a toolpath is planned for the inspection process. The robot then switches sensors to start inspection along the planned path. TNO developed an innovative, non-destructive ultrasonic inspection technique called direct velocity mapping, or DVM. An ultrasound transducer emits sound waves through the panel, which are measured by a MEMS array. The panel's shape is also recorded optically. Signal processing extracts the speed of sound, converting it into a thickness map. The system provides real-time updates, QA information, and integrates the thickness map into the digital thread for NDT inspector evaluation. This fast, dry, contactless, and single-sided ultrasonic inspection method detects disbonds, delamination, and weld defects. DVM is 10 times faster than conventional ultrasonic inspection, minimizing production disruption, offering significant time and cost savings. Airborne specializes in the automation of composites manufacturing. Accuracy of placement is increasingly important, and therefore Airborne has developed closed-loop control with affordable vision technology. When laying down a ply that is held between a mold and end effector, using a camera is often very limited. In the PeneloPe project, Airborne has implemented closed-loop control for the placement of stringers. Before final placement, the position is checked, and if necessary adjusted according to product references. This way, product and robot inaccuracy are eliminated using a digital, flexible, and fast process. Using closed-loop control, the placement accuracy is increased by a factor more than 10 to tenths of a millimeter. KVE has adapted their existing patented induction welding technology to perform single-sided welding required using conventional welding jigs. A welding tool was developed where all the complexity and mechanical elements were placed on a single side to allow cost reductions. ESI has developed a CAE solution to simulate the induction welding process for industrial parts, from the eddy current to the temperature evolutions in the parts. The simulations are first used to support the design of the process and establish its baseline for the production. Traditional CAE simulations take hours and are not compatible with inline prediction during production. To address this issue, ESI has developed meta-modeling methodologies for inline CAE-like prediction. This inline module is trained offline with numerous simulations. Using induction heating, a heat-up run is performed to get calibration data for the modeling. The results from the heating test are transferred to the ESI model. Based on the temperature data from the sensors, the inline module of ESI predicts the complete temperature evolution in the parts, then evaluates the specific weld parameters. A welding run is performed using the parameters generated using the modeling by ESI. The results from the welding process are transferred to the ESI model. The welding data is captured. Using the uploaded data, the temperature can be evaluated. Again, based on the real temperature data getting during the process, the inline module of ESI predicts the complete temperature evolution in the parts, highlighting potential risk zones needing further NDT inspection. The welded panel is ready for further inspection and processing. NLR developed a non-contact, non-destructive automated inspection based on infrared thermography. Production anomalies such as delaminations, voids, and foreign objects in the fuselage skin can be detected, aided by fast interpretation of multi-domain inspections using AI. The system reports progress information, returns inspection images, and locations of suspected anomalies for the NDT inspector to assess. The automated thermography inspection is 10 times faster than conventional ultrasonic inspection, saving valuable production time and material. Fokker Aerospace developed a fastening system with cobots. One cobot installs and removes temporary fasteners that clamp drilled parts together during assembly. Cobot force control creates a safer environment for nearby operators and prevents damaging delicate aerospace products. The sensors embedded in the cobots allow for surface-guided feature location verification. Unweldable parts are assembled using high-strength fasteners installed by the second cobot. The system receives data about the planned operation and fastener storage content. System status, operation progress data, and the found hole positions are fed back to the digital thread. This enables closed-loop learning to improve system productivity and design comparison. TNO has developed a solution to enable milling processes to begin with a 3D additive manufactured part. First, the bracket is scanned using a high-precision 3D camera mounted on a robot. The scan is used in a digital workflow, which automatically aligns the coordinate systems of CAD, machining, and camera frames. This step produces a calibration file and altered machining code. The outputs from the workflow is then used on the machine as normal. This solution simplifies the alignment process of complex 3D welded shapes on milling stations, saving a significant amount of time. The PeneloPe project enabled GKN and their industrial partners to demonstrate technology developments in a full-scale pilot setup, connected via a digital thread. Achieved by increased positional accuracy by laser tracking, virtual process simulation, locating objects by 3D scanning, novel non-destructive inspection methods using AI, automated stringer pick and place, improved induction welding by parametric modeling, automated fastening using cobots, and a workflow to mill parts out of additive manufactured blanks.